Alright, let's evaluate our model. At first we check whether a GPU is available. Typically in PyTorch you define a variable called device and then use torch.device, which is either CUDA:0 if torch.CUDA.is_available, else we assign CPU. This statement checks whether a GPU is available and if so uses it. Otherwise it uses the CPU. Next it is time to load the checkpoint. Let us override our model variable and then use pneumonia model.load_from_checkpoint and pass the path to the checkpoint. The weights are stored in a directory called weights, and you can choose between weights_1 or weights_3. Weights_1 corresponds to the parameters of the network which was trained without using a weighted loss, whereas weights_3 correspond to the network which was trained with a weighted loss of 3. Let's start with weights_3. Next, we need to set the model to evaluation mode. Finally, we can send the model to the pre-computed device. When calling model.eval, PyTorch automatically prints the summary of the model. You can add a semicolon behind this statement to prevent it from doing so. Now we compute the prediction on a complete validation set and store the predictions and corresponding labels. At first we define two empty lists called preds and labels, and next we use with torch.no_grad to prevent PyTorch from storing the gradients. The gradients are not necessary here because we only want to compute the raw prediction. Next we loop over our validation dataset to access the X-ray images and corresponding labels. Additionally, we use TQDM to get a nice progress bar. Now, as we are not working with PyTorch Lightning anymore, we need to manually copy the data to the device, convert it to float, and add the batch channel dimension. In code, we need to write data equals to data.toDevice.float to convert it to float, and .unsqueeze0 to add the batch axis in front of all other axes. We can now compute the prediction on this particular X-ray image. Let's directly convert the raw model outputs from model of data to probabilities by using torch.sigmoid. Additionally, we remove the batch channel dimension again and also copy the output to the CPU. Let us now append this prediction to our preds list and also the corresponding label to our labels list. Last but not least, we convert both our prediction and our labels list to a torch tensor, which allows us to use torch metrics again. We therefore write preds equals to torch.tensor preds and labels equals to torch.tensor labels.int. If you remember, torch metrics always wants the labels to be of type integers. When running the cell, the complete evaluation routine is performed. Let us now compute several metrics. At first, we should take a look at the accuracy to get an overall intuition how well our model performs. Next, as our dataset is imbalanced, we absolutely have to inspect precision and recall. Those values tell us whether our model has a problem predicting one of the two classes. And last but not least, we can compute the confusion matrix. To compute accuracy, we can use torch metrics.accuracy and pass our prediction and labels tensors. To calculate the precision, we use torch metrics.precision, where we also pass our breadths and labels tensors. Additionally, we perform the identical operation to compute the recall. Last but not least, we want to obtain the confusion matrix. To do so, we call torchMatrix.confusionMatrix. Please note that in contrast to the other metrics, you need to pass the number of classes, 2 in our case, to the corresponding constructor. After that, we can pass breadths and labels again. We can now write several print statements to take a look at all computed metrics. At first, we print our accuracy. Next, the precision and recall. And last but not least, the confusion matrix. Okay, let's talk about those metrics for a second. We get an overall accuracy of about 76.5%. However, this value is not very meaningful because it doesn't tell us whether our model has problems with pneumonia or with images that do not show signs of pneumonia. Therefore, we have to take a look at precision and recall. We can directly see that the recall is much larger than the precision. The high recall tells us that our model rarely misses a case of pneumonia. However, the low precision means that many images without pneumonia are also classified as pneumonic. This can be further verified by looking at the confusion matrix. It shows us that 1,537 images were correctly classified into class 0. In contrast, 517 images were correctly classified as pneumonic. Only 88 pneumonias were missed. However, this comes with the cost that 542 X-ray images were incorrectly classified into class 1. We have a low false negative rate but a high false positive rate. It always depends on the case whether such a result can be considered good. In this case, I would argue that it is better to have a higher false positive rate than to miss too many pneumonias. Last but not least, we can rerun the complete evaluation with the model which was not trained with a weighted loss. To do so, we simply replace weights_3 by weights_1. After that, we only have to rerun those 3 cells. This model yields a much better accuracy, but a significantly worse recall. It fails to detect a sufficient amount of pneumonias. You can also see this in the confusion matrix. 271 pneumonias were misclassified. You just built and evaluated your first PyTorch Lightning model to tackle real-world medical imaging problems. Congratulations! In the next lecture, you will learn how to visualize the regions in the images that are relevant for the decision of the classifier. Thanks!